This video is part 2 of section 3.4, Random Variables. We're going to look at some real-world examples of random variables and expected value. Suppose in fall 2024 there were 3,000 students taking an introductory statistics class at a large university. This class required a textbook and recommended a study guide. The university bookstore sold both books. Not all students bought both books from the bookstore. So let's assume that the university collected data on all of these 3,000 students. On the right, I have a snapshot of the data. So here we have 8 students and their student numbers, whether they bought the textbook or not, and whether they bought the study guide or not. And you can see, for example, in row 2, we have a student who bought both the textbook and the study guide from the bookstore, while student 3 in the row 3 bought the textbook but not the study guide. And in row 4, we have a student who bought the textbook and not the study guide. But row 5, we have a student who didn't buy either book. So you can assume maybe they bought it on Amazon or some other location for the book, or maybe they just didn't buy the book at all. For us, because we're going to assume that the textbook is required, but the study guide is not, we'll assume that they can buy the textbook alone, but they can't buy the study guide alone. It doesn't make sense for a student to buy just the study guide if they don't have the textbook, okay? So they're either going to buy the textbook, both the textbook and the study guide, or neither. So on the left, I have a little table that says how many students bought neither book, and 600 of the 3,000 bought neither book, 1,650 bought just the textbook, and 750 students bought both the textbook and the study guide from the bookstore. And then I have a little bar chart here that tells us visually how many students bought each option. So neither book, just the textbook, and the textbook and the study guide. So it makes sense for a company like the bookstore or the university to wonder how many books they need to order for next semester, or how much money they expect to generate with revenue from students buying books. So those are the types of problems we're going to look at in this PowerPoint presentation. So notice that I can take these numbers, like the number of students who bought neither book, and I can make it into a percentage. So 600 of the 3,000 students didn't buy a book. So that is 20%. You can put it into your calculator and check. That's 20% of the students didn't buy either book from the bookstore, while 1,650 over 3,000 is 55%, and 750 over 3,000 is 25%. And so I can take this bar chart where the frequency is the y-axis, and I can make it into a relative frequency. So I can make percentages, or I can write the percentages as decimals as the y-axis. So I get the same graph, it's just that I'm scaling the y-axis a bit. Instead of the y-axis being the number of students, it is the percentage, or in this case, you could think of it as probability. Now let's allow X to represent the number of books bought by a random student at the bookstore. What is the range of X, and what is the probability X is equal to 0? So if X represents the number of books, and they're going into the bookstore, they're either going to buy neither book, one book, or 2 books. So that is the range. As for the probability X is equal to 0, that means that they didn't buy any book, and 20% of the students didn't buy either book. So if I randomly choose one student from the 3,000 students, the probability that they didn't choose a book is 0.2, or 20%. Now we can make a probability distribution. Notice the difference between this bar chart on the right versus this bar chart. So what I've done is, instead of putting neither book, textbook, and study guide, I'm changing it to x0, 1, and 2. So it's the same chart, it's just that I'm thinking of these instead of having categorical data, I'm thinking of it with numerical data. And I can make a table to correspond to this bar chart here. So we said that x could be 0, 1, or 2. And we said 20% of the students didn't buy either book, 55% bought only the textbook, and a quarter of the students bought both the textbook and the study guide. Again, this is a valid probability distribution because if we add 0.2 to 0.55 to 0.25, we will get 100%, or 0.1 is the same thing as 100%. You can't buy no books and also buy a book. So these are disjoint events, 0, 1, and 2. And all of the probabilities are between 0 and 1. Those were the 3 rules for a probability distribution. Now let's find the expected value of x and interpret its meaning. So recall that to find the expected value, we take the x value and multiply by the probability for each x value, and then we just add those numbers up. So we're going to take 0.2 and multiply by 0, 0.55 and multiply by 1, and 0.25 and multiply by 2. And you should get 1.05. And that is, remember that x is the number of books bought by a random student, so we expect 1.05 books per student. What does this number really mean? Now, no student is going to go in and buy 1.05 books, right? It's impossible. You're either going to buy 0 books, 1 book, or 2 books. But what this means is that if we see how many students, like let's say 30 students come in, what's going to happen is they're either going to buy no books, 1 book, or 2 books. And if we just write how many books they bought each time, like Jill bought 1 book, Sally bought 2 books, Tony bought no books, and then we add all of the number of books that all these people bought and divide by how many students came in, it should be close to 1.05. Now, suppose the percentage of books sold each semester stays relatively constant. If there are 4,200 students that are signed up to take this class in fall 2025, and let's assume that it still requires the same textbook and the same study guide, how many books should the bookstore expect to sell? This is a good question because they need to know how many to purchase in order to sell. You don't want to have too many books. Maybe you could sell them the next semester, but sometimes books requirements change. So you want to have the right amount of books because they take space and you could use that space for selling other things. So you don't want to buy too many books and you don't want to buy too few books. So how many should we expect to sell in fall 2025? Whenever we see the word expect, we should think expected value. Okay, and so we already found the expected value. We said that the expected value was 1.05, and that's per student. So if we take 4,200 and multiply by 1.05, that will tell us about how many books we should expect to sell, which is about 4,410 books if there are 4,200 students in the fall 2025 semester. Now let's suppose that the textbook costs $137 and the study guide costs $33. Let Y represent the cost of the book bought by a random student. Well, if we think of it this way, we can say that Y, the range of Y, is 0, 137, or 170. Remember that they're not going to buy the study guide by itself. So they're either going to buy the textbook, no books, or both books. And if they're going to buy both books, we have to add 137 to 33, and we should get $170. So those are the 3 options. And again, we saw that 20% of the students bought neither book, so they spent no money. 55% spent 137, and 25% spent 170. Now let's calculate the expected value of Y and interpret its meaning. So we're going to do the same thing we did with the expected value of x, it's just that our y values are different. So we're going to take 0 and multiply by 0.2, 137 by 0.55, and 170 by 0.25. We'll get 117.85 per student. And what this means is that all of the students who come in, if we write down how much each student spent, it should average to about 117.85. How can we use this piece of information? Well, imagine if we want to know how much revenue we expect to generate from the next semester, the 4,200 students. Well, we can take 4,200 students and multiply by the cost, well, how much each student spends. Roughly, they spend 117.85 on average. So then we just multiply these two together and we get about $494,970. So that's how much revenue we should expect from these students. Let's try a new example. Suppose a company plans to invest in a construction project. Past data from similar construction projects suggests there's a 35% chance the project will result in a loss of $30,000. There's a 40% chance that the company is going to break even, meaning they don't gain or lose money. And there's a 25% chance the project will result in a profit of $55,000. How much can the company expect to make or lose on this project? So if we allow x to represent the projected loss or profit, the range of x has three different options. We can either lose $30,000, and I put a negative here because that means we're losing the money. If it was positive, we would write positive 30,000, and that would mean we'd gain $30,000. The negative means we're losing. Breaking even means we make $0, and a profit of 55,000 means a positive 55,000. So these are the three options here. We can make a probability distribution because there's a 35% chance we lose 30,000. That's why we got 0.35 under the negative 30,000. 0.4 under the 0, and 0.25 under the $55,000. That's all from the problem. And so our question was, how much can the company expect to make or lose on this project? Expect means expected value. So the expected value, this should say expected value of x, but the expected value of x is negative 30,000 times 0.35 plus 0 times 0.4 plus 55,000 times 0.25. And if you add all of that up, the expected value is $3,250. What does that mean? We do not expect that we will make exactly this amount of money on this particular construction project. Instead, if we were to make this construction project several times, like throughout the city, maybe we had, or throughout the country, we had to make this construction project. On average, sometimes we're going to lose money, sometimes we're going to gain money, sometimes we're going to break even. But if we added all of that up and divide by how many times we had this construction project, we would expect that each one would bring in about $3,250. So maybe in the long run, it makes sense to have a construction project, to go through with this construction project. If in the long run we were getting a negative number, it wouldn't make sense to go through with this construction project. Let's try one more. Let's say we play a game where we pay $1 to spin a wheel numbered 1 through 10. If the wheel lands on 8, you're going to get $5. So you're paying $1 to play, and you're going to get $5, which means you make a profit of $4. If it lands on any other number, you lose and you get $0. That means you're paying $1, you lose your money. So you make $4 if you land on an 8, and you lose your dollar if it lands on any other number. Let X represent the net change in your money after one round. In other words, what are your profit and losses? And then I also want to know, what is the expected value of X? So here's my table. That is my probability distribution. There's two things that are going to happen when I play this game. I'm either going to lose my money or I'm going to gain $4. The probability that I lose my money is 9 out of 10 because this wheel is numbered 1 through 10. So assuming that when I spin the wheel, each of the blocks that have the numbers are the same size, 9 times out of 10, I'm not going to land on an 8. While only 1 time out of 10, I'm going to land on an 8. So only 1 time out of 10 am I going to make that $4. And 9 times out of 10, I'm going to lose $1. So the expected value is -1 times 9 over 10 plus 4 times 1 over 10. If you add that up, you get -5 over 10, which is -0.5. So I expect to lose 50 cents if I play this game. What does that really mean? Because I will only lose $1 or I will gain $4. What this means is if I played this game several times, I told them I want to spin the wheel 100 times, and I lose my dollar or I gain $4, and I just add up my winnings and divide by the total number of times I play, I'm going to lose 50 cents. This game is rigged for me to lose money in the long run. So I would say that I wouldn't want to play this game. Maybe there's a small chance that I'm going to win, but there's a bigger chance that I'm going to lose. And the way that this game is structured is so in the long run, I am losing money. So I don't think this is a good game to play.